So this is lecture 15, and in this lecture is when we get to talk about the search for intelligent life in the universe. This is going to be a lot of fun, but also an incredible amount of speculation because we just don't know that much about it. In the final lecture, the lecture after this one, we'll talk about something that's a little bit more tangible, and that'll be the search for life, period, in the universe and how we might go about doing those kinds of things. Okay. So, you know, when we talk about the idea of intelligent life, things get a little bit tricky because then you have to actually define what intelligent life is. And, you know, remember in the very beginning of the course, we spent a long time fiddling around trying to actually define life, and we sort of came up with a couple of ideas that you might start working with. Intelligent life is probably even harder to define, but since we want to talk about intelligent life, it's at least worth, you know, talking about, you know, trying to come up with some kind of context for what we mean by intelligent life. I think, broadly speaking, when we talk about intelligence, you know, we might be thinking about sort of higher thought that, you know, you sort of, you know, the general ideas that drive life, right? So you want to eat, survive, and reproduce. That's basically what life does. And, you know, the forces of evolution make pretty much all life good at that, right? So the very fact that your species exists means that you're very good at eating, surviving, and reproducing, okay? The thing that's sort of weird that you know, if you think about what humans do, it's that we spend some considerable amount of energy thinking about things that aren't tangibly related to us really surviving or reproducing or eating or doing any of those sort of basic things that sort of keep us alive. Why we actually do that, it's sort of weird. Like, what is the evolutionary pressure that it has, you know, pushed us to do these kinds of things that you might think about as sort of wasteful? So we'll talk a bit about that. So, you know, here's a sort of an example of how we might go about trying to define a living being that is intelligent. And by the way, you know, people also talk about whether or not it actually has to be a biological being that's intelligent. You know, people talk about artificial intelligence and whether or not in the long run, you know, if we advance to the point where we can actually build machines that are themselves effectively alive because they would follow up on these ideas. So for example, an intelligent being has self-awareness. It asks questions like, what is it all about? Why am I here? Is there life elsewhere in the universe? These kinds of things that don't immediately affect us in our day-to-day lives. Intelligent beings perhaps use tools to manipulate their environment. So we certainly do that all the time. I mean, our society is built around the use of tools that allow us to sort of be here and do the things we're doing in this room. A very important thing that at least our species does is it uses language, and this language is incredibly powerful, right? Because it allows us to communicate thoughts with other intelligent beings. It allows us to teach complex ideas to each other. And so then, rather than a single individual having to figure things out for themselves, they can actually learn from each other, and things become cumulative, and that allows a society to be sort of an intelligent society. The thing that makes this a little bit complicated is that there are, of course, other animals on Earth that do these things. And the question is, would we classify them as intelligent? That is, if we discovered, for example, dolphins swimming underneath the ice of Europa, would we say, aha, we've discovered another intelligent species? You know, maybe we would say yes. I mean, we know that dolphins do communicate with each other through sort of signature whistles. And it's a pretty complex thing that they do. We know that chimpanzees and bonobos use tools. They modify sticks in such a way that they can then stick them into termite holes and get termites for themselves to eat, right? So they do things, you know, there are animals that do things that we would classify as pretty high level activities. The other thing that intelligent beings do is they hand down behaviors to their offspring. So you're getting things from your parents besides just their DNA, right? Your parents teach you how to do some things, and then more broadly speaking, you learn from the society you're within. to do things that you otherwise maybe you couldn't have figured out on your own, or it would have taken you sort of an impossible amount of time to figure out. So for example, dolphins teach their children how to use sponges to protect their snouts when they're doing certain things. Chimpanzees teach their children how to use stones to crack nuts. And it's a behavior you'll see. You'll see sort of an older chimpanzee using a stone to crack a nut. The younger ones watch this, and it's a learned behavior. One of the things, for example, though, that really sets human children apart from the young chimpanzees, for example, is their ability to sort of mimic and learn. So they've done interesting experiments comparing sort of like 3-year-old kids to sort of equivalently aged chimpanzees, youngsters, and they'll find that actually, if presented with a problem, oftentimes the chimpanzees will solve those problems more quickly than the human kids will. But they'll do other experiments where they will actually show the pair how to do something, like a trick to open a box to get like food out of it. And the human kids are really good at that. So it turns out one of the things that really separates the humans from the chimpanzees is not necessarily the innate intelligence to figure things out for themselves, but their ability to watch other people and learn tricks and then adapt those tricks to their own devices, right? And we're all very good at adopting other people's tricks, right? So most of us didn't invent many of the things that we're using right now. We sort of adapt other people's tricks, and then you make just an epsilon improvement on those things, and then that's what allows for this advancement. One of the things, of course, that allows for this in a sort of more complex way is language, right? So language is a very helpful tool in transmitting culture and complex information from one person to a next, whether or not that's necessarily verbal language or sign language or some other form of language. High-level language is a very important thing that at least humans have developed that allow them to do lots of stuff. And we don't know exactly when language first developed in early proto-humans, but there are some people who believe that it stretches back earlier than 1 million years ago, that proto-humans were using effectively talking to each other very, very long ago, and this is one of the things that allowed them to survive. Of course, it's very hard to get evidence of that. The thing that we do have evidence for, though, is written language, specifically when the writing is left in stone tablets, the stuff that survives for a long time. And specifically, at first there's sort of hieroglyphic type language where you just have symbols that stand for things, and eventually these symbols start to represent sounds, and you can begin to build sort of proto-alphabets. We certainly have strong evidence for written records dating back to 3000 BC. The Sumerians are some of the oldest recorded written language. This is actually a tablet that records an allocation of beer in this particular area of what is now southern Iraq. So, they were doing very important things with their language. You've got writing apparently developed independently in different parts of the world. Here's an example of early writing that was developed in Mesoamerica. Ancient Mayan civilization had writing of their own. This is circa 1000 BC. But of course, the Mayans and the Sumerians were separated well before, the people who came to the Americas crossed over the land bridge probably around 16,000 years ago, well before writing existed in any population. And so it seems as if writing actually developed independently in these two civilizations, as well as agriculture and many other things developed independently. So another thing you can look at is just the sort of basic physicality of intelligence, and one thing that people look at is something called one thing that people look at is if you measure the mass of an animal's brain and compare that to the body mass, you can see how much you're devoting to your brain. And so that's sort of a crude thing that allows you to sort of ask how intelligent the species is. So what's plotted here is the brain mass versus the body mass. And as you see, while humans they certainly do not have the biggest brains in the animal species. There's whales that sort of have bigger brains than humans. The ratio of brain mass to body mass gives you a sense of sort of what an outlier this kind of animal is. And humans sit well above the trend for different kinds of animals. Primates are black points here, and you say generally primates tend to lie high on this line. This is just an old figure that I found just because it just labels actually specific things. Here's an elephant, right? An elephant actually, certainly has a more massive brain than humans do, but for its body mass, a human has sort of an anomalously big brain. When you actually take these two numbers and divide them by each other, that is, you take the mass of the brain and you divide it by the typical mass of a brain you should have at that body mass, okay, that's called the encephalization quotient. So you take the brain mass, you divide by the average brain mass for that body size, okay. Humans have a very big EQ, okay, so we have very big brains compared to how big our bodies are. Dolphins also have a pretty big EQ, but not as big as humans. Chimpanzees are also pretty big. Cats and dogs are pretty typical. So most animals have sort of, typical brain to body ratios of cats and dogs. And then you can go down to things like goldfish, who are, sort of notoriously dumb, and they, of course, have small brains. Now, of course, I'm just sort of course, there's the joke about the goldfish. Every time it sees the castle, it's a surprise as it goes around the, and that's sort of and they do seem to be not the brightest things in the world. But one thing to keep in mind, on an object-by-object basis, the size of your brain doesn't tell you how smart you are, okay? So, in a human population, you can't just weigh someone's brain and be like, oh, that person's got the biggest brain, so they're the smartest. It doesn't correlate like that at all. This is just more like a gross characterization of the species. It's saying, look, this species in general devotes a lot of energy, a lot of caloric energy to keep that brain functioning. So for whatever reason, intelligence is valued in this species. So, but it's sort of dangerous to start thinking of like, boy, if I have the biggest brain, I'm the smartest person. That's not true. It's more like just sort of gross species comparisons here. One thing that is sort of generally true, though, is if you just sort of take a look at these animals, you have this sort of qualitative feel that, yeah, it does sort of seem like dolphins and chimpanzees are smarter than cats and dogs. And it also certainly seems that cats and dogs are smarter than goldfish. Whether there's a direct correlation, you don't know. And we like to think that humans are smarter than dolphins and chimpanzees. So it sort of makes sense in this way, right? However, this is sort of something to keep in mind. Intelligence can, give you an evolutionary advantage. Obviously, there's some evolutionary advantage to being clever, okay? However, you expend a lot of energy if you have these big brains. So in humans, our brains use 20% of our caloric energy. So if you're in a survival situation and food levels are very low, you might argue it doesn't make a lot of sense to have a brain that's using 20% of your energy just to sort of be, right? Rather than to go and get new food or do whatever you need to do to stay alive. And so you have to have the very correct conditions to allow an animal like this to even exist that's wasting 20% of its energy just thinking and thinking about the sky or something when tigers are all around you. Okay. The other thing to keep in mind as we start thinking about intelligent life throughout the universe, it took nearly 4 billion years from the origin of life on Earth for the rise of modern humans. Okay. So this is the last 4.6 billion years on Earth. 4 billion years ago, 3, 2, 1, 0. Homo sapiens evolved something like 200,000, 100,000 years ago. So they're at the very edge of this plot, right? Eukaryotes, okay, evolved here. Multicellular life first existed only 2 billion years ago, right? So it takes almost 2 billion years to get multicellular life. Another big chunk of time to get eukaryotes, these more complicated cells, cellular-based life. And then finally, animals are evolved in here. So let's zoom in onto just this last bit. Okay, the last 600 million years, right? The first fish evolved like 550 million years ago. These are your goldfish, right, with the tiny brains. 550 million years ago type things. Land plants and animals were only here. Even dinosaurs, which we think of as ancient, have only been around, were only around about 250 million years ago. Okay? The first great apes were here at the very edge. And again, Homo, the genus Homo, is at the very edge of this plot. Okay, and then finally, the last 250 million years, you can start to see a little gradation here in the last 50 million years. You know, the first great apes were here at the edge, but again, you know, our species only evolved at the very, very edge of the history of life on Earth. And so to have this idea that intelligent life should be prolific, maybe not, because it took quite a long time on Earth for these upright apes to start, doing things. However, there does seem to be a pretty significant evolutionary advantage to whatever thing we've managed to do, right? This intelligence and combination of language, intelligence, technology that we've managed to cobble together over the last 100,000 years or so has been extremely advantageous, especially, in the last several thousand years. So if you look at the human species and population over time, and this is a very sort of recent time, it's certainly spiking right now. We've figured out how to tap into energy sources that go well beyond the energy sources that are just delivered to the sun. We're tapping into deeper energy sources that allows us to grow more food, right? And we grow all this more food, and so we can have these bigger populations, so we have these stable populations, right? And so they're just spiking up right now, right? So intelligence is at least an advantageous trait in that sense, right? We're smart enough now that we don't really have any predators. We figured out how to feed most of our population, and of course we're struggling with hunger in a lot of the world, but there are technological advances that are allowing us to sort of do better on that. And so there's so many things that intelligence has provided an advantage to the bulk population. Of course, also human intelligence, we're so smart that we're able to do things that are pretty radical, right? So we're in the position where we might be doing things to eventually destroy the world that we inhabit if we let that technology sort of get out of hand, right? And so people talk a lot about nuclear holocaust. We talk a lot less about that these days. But of course, we have developed weapons that allow us to basically destroy cities and kill millions and millions of people at once if such an event happened, right? So sometimes intelligence can be a disadvantageous trait. And there's some concern, of course, that because we have tapped into this energy source, which is fossil fuels, we're putting all that carbon back into the atmosphere that took sort of so long to come out, that this will also cause global climate change, that will also affect our ability to sort of survive and maintain this very strong rise in population, which is of course correlated with rises in technology, et cetera, right? So, more people provide an increase in the economy, which spurs innovation, which spurs new technology, which allows these advances to happen. If there's something that eventually shuts this down, you might think that, well, then the technological rise is also going to shut down. The other thing to keep in mind is that high intelligence plus, say, opposable thumbs or whatever you need to build tools might not inevitably lead to this kind of advanced technology, right? There are a number of things that kind of had to come together for us to be able to sort of tap into this technology and these energy sources, et cetera. I mean, for example, 30,000 years ago, okay, if you went and you were talking, you were interacting with a Homo sapien, they would look exactly like you. Okay, there would be surface features that are a little bit different, but they were just as smart as us, as far as we could tell. Their brains were just as big. They were very intelligent people, right, living 30,000 years ago. Okay, but they didn't immediately begin building spaceships and radio telescopes. Okay, they were doing other things. So even within that context, it took a very long time for these kind of advances that would allow you then to be visible to distant civilizations to occur. So when we talk about the search for intelligent life, what we're really searching for most of the time is advanced technology, and that's not a one-to-one statement. Okay. There are a lot of very intelligent civilizations that have existed in the history of the world, right, that were thinking very advanced thoughts that didn't have spaceships, right? They weren't building telescopes. Okay? So you can imagine, for example, a world of Zen monks, right, that were way more enlightened than all of us, thinking very complex thoughts or whatever. They're not going to be building, spaceships and making reality TV shows and then broadcasting those reality TV shows out to the world. Okay, so when we think about looking for intelligent life, we have to be careful of what we're talking about. So it could be an anomaly, right, that we've sort of sprung forth and become this, so most of the world is sort of building these kind of technologies. That might be an anomaly even for an intelligent civilization or an intelligent species. So, so then we can ask ourselves, well, what if we were looking at ourselves from afar? Would we qualify ourselves as intelligent beings with advanced technology? Okay, so if you now took a lens from some civilization, for example, maybe it develops on a star that's 4 billion years older than the sun. So they've been around a very, very long time. And they come across this planet around this G-type star that's doing these kind of weird things. They might wonder whether or not this is a civilization that's worth contacting. Okay. Now, what do we mean by advanced technology? We just need to define it in some way. You can set different bars for what you mean by advanced technology. But one thing you could say is, well, advanced technology is the ability to send out, for example, radio signals, or perhaps some other kind of signal, and build interstellar spacecraft. So if this was your criteria for what, if these were your criteria for what you need to be an advanced technological civilization, we have only very recently qualified as advanced. Right? That's pretty clear. We have, had limited short duration piloted spacecraft for only 50 years, right? And we really haven't gone anywhere, okay? We've gone to the moon, right? I mean, that was kind of awesome. It's amazing that we went to the moon, okay, rah, rah. But the moon is pretty close to the Earth, and it's certainly really, really far from the nearest star. So to call ourselves an interstellar civilization is ridiculous. Like, we're clearly not an interstellar civilization. We've never sent anything to another star, much less a person. Okay. We've had radio communication technology for about 100 years. So what this means is that there's a bubble of about 100 light years around the Earth. Any star within that bubble has seen our radio, potentially could have seen our radio broadcasts, right? So old TV shows would be sort of out there, right? 50 light years away, it's something like I Love Lucy is sort of just getting there, right? However, if you take a step back, there are lots of reasons to think that intelligent life with advanced technology exists elsewhere in the universe. And the biggest argument, in my opinion, the strongest argument for that is just the sheer number of opportunities that we have. Okay, so there are about 100 billion galaxies in the observable universe. So each dot, each little thing on this plot here, in this picture, that's these are galaxies. Each of these galaxies has something like 100 billion stars. Okay, so it's just a chunk of the universe, just a piece of blank sky. The Hubble Space Telescope pointed at it, took a very deep picture, and it's just filled with galaxies, right? Each of these galaxies has about 100 billion stars, okay? And so you're talking about 10,000 billion stars, so 10 to the 22 stars in the observable universe that are potential sources for other intelligent life. So this argument alone makes it seem like, well, this is a lot of chances. And so this is one of the reasons why many people believe that, we're probably not alone in that sense, that there's nothing else in the universe that is intelligent. But we do not know that for sure. So even if each star has a 1 in a trillion chance of hosting an advanced civilization, there should be billions of advanced civilizations in the universe. So let me pause here. I've talked about it. Are there any questions or comments about any of this stuff? Okay. So if there's anything that comes up, please raise your hand. If you disagree with anything I say, please raise your hand. Because we're getting to this point where it's becoming very subjective. So I'm just sort of throwing ideas out there for discussion more than anything. Now, if it is true, and this is a totally made up number, but if it is true that there's a 1 in a trillion chance of hosting an advanced civilization around each star, we're probably the only one in our galaxy. Of course, our galaxy only has 100 billion, 200 billion stars in it. So if the chances are 1 in a trillion that each star has an advanced civilization around it, and we call ourselves advanced, we're it. And our galaxy is pretty big. Okay, so we are in a pretty lonely place if that's the case. Now, there's a famous equation that an astronomer named Frank Drake wrote down that allows us to kind of quantify what we might expect the number of communicating civilizations would be in our galaxy. Okay, and his equation is called the Drake equation. And here the term advanced civilization is defined as one that can communicate across space, that we might be able to detect their signals being beamed at us, perhaps in the radio. Here is the Drake equation and what it is. Basically what the Drake equation is it's a way to quantify our ignorance about this question that we know so little about. Okay? But what it's trying to do is it's trying to estimate how many other, or in total, communicating civilizations there are in our whole galaxy. Okay? And the way it works is this. So basically, to get this number, you're multiplying a lot of things together. Okay? The first thing you multiply out is the number of stars that are made in our galaxy every year. Okay? So maybe there, and we actually have a reasonable idea of what that number is. And it turns out that every year our galaxy makes between 5 and 20 stars, roughly, per year. So we have a sense of that. Now, it's the number per year, and I'll come back to why. But basically, this is just telling you, okay, look, if I just have a snapshot this year, how many new stars are born? Every new star that's born, that increases the chances that some communicating civilization is going to exist. Okay, that's a way to think about it. Then you multiply that by the fraction of stars, the fraction of any star, of any of those stars, that's going to have a habitable planet. Okay, and that's a number that we actually are starting to know, right? I've talked to you about in the last lecture about we're actually now to the point where we can determine the fraction of stars that can have these habitable Earth-like planets. And we think that that number is somewhere around 20%, but I'm going to give it a little leeway and say it's somewhere between 10 and 30% of these stars that are made are going to have habitable planets around them. Now, then you multiply that by the fraction of those habitable worlds that actually have life. And that is a very big unknown, right? We don't know what that is. It could be basically 0%, 0.1%, it could be 100%. Okay, we don't know that answer, but that's just sort of, so that number could be anywhere between 0 and 100. Then you got to multiply that by, of those worlds that actually have life, the fraction of those that evolve intelligence. And again, even if you've got life, it doesn't mean you have intelligent life. It took 4 billion years for that to happen on Earth. So again, that could be between 0 and 100%. 100% there seems extremely optimistic to me. I would think it's got to be much lower than that. Finally, you multiply that by the fraction with communicating technologies, right? So it's this question of whether you have intelligence and whether that intelligence actually means you have communicating technologies. It doesn't necessarily mean 1-to-1. So you can multiply that out. Again, that could be between 0 and 100%. And finally, and this is sort of the piece that ties it all together, it's the lifetime that advanced civilization will exist. Okay? So what you've got here is you've got a rate, basically, the number per year that are happening. And over here you have a length of time, the number of years that these advanced civilizations will persist. So this acknowledges the fact that these civilizations will not last forever. Now, of course, we don't know what that typical number is, and I'll talk a bit about what these numbers are. And so what you do with the Drake equation is just sort of an exercise, is you come up with good estimates for each of these numbers, and some of them you're wildly uncertain, and you multiply them all together and you get a guess for how many communicating civilizations there are in a galaxy. Yeah?
On the number of stars made per year in our galaxy, when those stars are made, are they expanding the area of our galaxy, or are they just filling up space?
Yeah, that's a great question. So the question is, when new stars are made in our galaxy, are they basically like making the galaxy bigger, or are they just forming within the galaxy as a thing? Basically, mostly, they're just forming within that region that is the galaxy. They're sort of new stars being born within the galaxy. There's a little bit over time, we think the galaxy has gotten a little bit bigger. So there is some evidence, or there's pretty good evidence, that over the course of sort of billions of years, galaxies start off small and get a little bit bigger. And so a lot of the new stars are formed in the outer parts compared to the inner parts. But especially these days with our galaxy, we don't think it's growing that much anymore, and most of the new stars are just forming within kind of that 100,000 light year diameter thing that we have. Yeah, that's a good question. Any other questions? Okay. Okay, here's me just making up some numbers here, just to see what we get, all right? So I'm going to say about 7 per year. That's how many stars are born in the galaxy. I'm going to say 20% have habitable planets. That's the number we get from Kepler. I'm going to just say 50% of those evolve life. I consider that a pretty optimistic number. I'm going to say only 0.05, so only 5% of things with life actually come up with intelligent life. But then I'm going to say, if you're intelligent, you're at some point going to build a telescope or some kind of communicating technology. So I'm going to say 100% of intelligent things are going to have communicating technologies. And then for the lifetime of that advanced civilization, I'm going to pick 100,000 years or 10,000 years. Why did I pick 10,000 years? I don't have a really good reason. You know, we've had communicating technologies for about 50 years. Okay, so we know it's reasonable to suspect that it's going to last 50 years. You might argue that in 100,000 years, it will be hard for us to come up with the energy requirements to continue to sort of send out signals. So, I'm just going to throw that in there. You might be optimistic and say this is going to be 1 billion years. Okay, and that'll increase the number a lot. But whatever, I threw these numbers down, and you're welcome to pick numbers that you like too, and see what numbers you get. But I got 350 civilizations that are communicating throughout the galaxy. Okay, are there questions about this? Okay. Now, this thing about the lifetime, I want to talk about this a little bit, okay? So, it's the lifetime that advanced communicating civilizations can exist, and it's sort of an uncomfortable question, right? Because when we talk about it, we're actually talking about, you put yourself in our shoes and we're like, whoa, how long are we going to last? Like, how long globally? I'm not talking about individual countries, I'm talking about the globe, the world. How long is the world going to have civilizations that are sending these signals out, right? Now, the lower bound is about 100 years, right? That's about how long we've had it. So you might think that's a reasonable lower bound. Upper bound, well, the Earth's habitable zone, the Earth is not going to be in the habitable zone of the sun in 1 billion years. Okay, the sun's luminosity is growing. The sun's getting bigger and getting brighter. And at some point, the energy output from the sun is going to be so high that it is going to create a runaway greenhouse effect on Earth. The oceans will boil, and it's pretty much going to be an end to civilization on Earth. Okay, so there's a good upper bound for us. Yeah, 1 billion years, 500 million years. That's sort of where things are going. Okay. Now, you can also sort of ask other things like, what's the average duration of empires and dynasties in the history of the world, right? Empires don't last that long, right? 1,000 years for an empire is like unprecedented. You have one country that's an empire for 1,000 years. That's a long time. So for individual countries, timescales of 1,000 years are long. Okay, so when I put down 10,000 years, I felt like that was actually reasonably optimistic. But you might be very optimistic and think, look, we're going to be this super advanced civilization. We're going to keep solving all the problems. We're going to keep doing whatever. And the only thing that's going to shut us down is when the sun gets bright. So we got 1 billion years. And then you could say, well, maybe by that time we'll just go to another star, because it's 1 billion years from now. Who knows what we'll be? Okay. So let's do a different number. If we would have put in only 1,000 years, okay, we'd only get 35 civilizations here. And so one thing I'm trying to say is, like, in principle, these are numbers that you could measure. And if you could actually go out in the galaxy, right, and have some kind of experiment that found all the communicating civilizations, if you knew this number was 35, right, and not 350, it might give you some sense of what our future is, right? If the universe is teeming, or that is, if our galaxy is teeming with advanced civilizations, okay, that would suggest that advanced civilizations last a very long time. If this number was, if this number was 1 billion years, this number would be big, right? It'd be 1 million times bigger. It'd be 350 million. Okay? So if you could go out maybe and do an experiment and ask how many communicating civilizations are there in the galaxy, that might make, and you found that number was huge. You just suddenly discover there's this whole Star Trek thing going on, and there's civilizations communicating with themselves all over the galaxy. That might make you feel pretty good about the future of our civilization too. But if we were to do an exhaustive search and we find nothing, that might make you feel a little nervous about this number. Okay, so if we made this 100,000 years, 2050. Okay. Now, of course, the Drake equation is not perfect. Okay, it's just sort of a rough example. It's a sort of thought experiment. It relies on lots of unknown quantities. It's basically a big conjecture experiment, but it sort of makes you think. It doesn't account for population dynamics, and it doesn't account for the possibility that you might colonize. Okay, like I said, maybe you might think, oh, our upper limit's 1 billion years. But maybe it's not, because we might, by that point, have gone to a nearby star and just started living around that star. Maybe we'd go to a star that's going to have a lifetime of 10 billion years. So we don't have to worry about that, right? So, in which case the numbers would only go up, by the way, if that's common. However, the nice thing about the Drake equation, it provides us with sort of a window for framing the problem and thinking about what things matter. Are there any questions about any of this stuff? Let me just take a show of hands here. Let me start with this. Let's say we've got a world that we discover that's clearly in the habitable zone. And let's say we even know what its atmosphere is, and so we actually know that the temperature of this planet is conducive for liquid water. What fraction of those worlds do you think will have life? Raise your hand if you think that that number is bigger than 50%. Really? Okay, raise your hand if you think that number is lower than 50%. Okay, so you think, okay, interesting. People who think, okay, raise your hand if you think it's less than 10%. Okay, so in this room, most people think that the number is less than 50%, but bigger than 10%. So 30% or so. For those of you who think it's lower than 10%, raise your hand again. Okay, why do you think it's so low? Yeah.
It just relies on a lot of things happening at once, like a reliable energy source and the right chemicals and some sort of liquid bath.
Okay.
Just a lot of things that might not happen the right way to produce stuff.
Okay. Okay, so you just think so many things have to happen to make it happen. I mean, one argument people could make against that is that, well, gee, on Earth it happened like that. It happened as soon as there was liquid water, we had life. You might say, yeah, but those are very special conditions. Does anyone have a different reason for why they think it's so rare? Yeah.
I was going to say, you can't predict that they all have had the time to have life, because like obviously, like it could be like the habitable zone.
Yes.
But if maybe it has an extra billion years, or in order order for life to form there.
Okay, so you're saying maybe it takes longer there. So, you're saying, well, it might be in the habitable zone, but it might take a little longer there than it does here. Even if we're looking at a star. So, okay, but let me just say, most stars in the galaxy are much older than 1 billion years. So if we're looking at an average star, if we found a planet around a star in the galaxy, in most cases, that thing's going to have been there much longer than 1 billion years. So it would have had more time to exist than it took life to evolve on Earth. Yeah?
Well, going about your first argument regarding water,
Yeah.
we still have an assumption that maybe it was a meteor who brought water on Earth, right? So that might not happen.
Yeah. You're saying maybe there's not water. Even if you could have liquid water, you might not have it.
Yeah.
That's a good point. I mean, one reason why people think it might be reasonably common is water is a pretty easy thing to form in nature. Oxygen likes to bind with hydrogen. So and we see water in space, like you see water like around stars and stuff like that. So, but you're right, it could be, there might just not be that much water or no water, even if it could be liquid. Yeah, one other thing?
Well, even with that argument, even if water is easy to form, maybe it's salty water from the ocean and not drinking water, so you might have life which might be completely in water, but not life like humans on land.
Yes, okay, right.
So
So,
there
yeah.
might be a different step. And then
Yes.
the other argument you were making about the longer time span.
Yeah.
So I mean, dinosaurs have were on Earth for a longer time than humans have been.
Yes.
And if it was not for their extinction 65 million years ago, we might not even.
Yes,
have had a chance.
right. So what you said, yeah, so just repeat so everyone can hear it. He said, look, this thing about time span, but dinosaurs were on Earth longer than humans have been on Earth, longer than humans have been on Earth, and they never made rocket ships and spaceships and stuff like that. So that's why I don't think it's inevitable. Let me just clarify, though, what I'm talking about. I was just talking about life. I think what you were getting into was this intelligent life thing, which is even harder. Okay, so just to sort of summarize, most people in this room seem to think it's less than 50%, more than 10%, maybe 30% for this number. So maybe I was a bit high compared to the rest of the room, which is interesting to me. You guys are probably right, because there's sort of this idea that crowds know the answer. So you're probably right, I'm probably wrong. What about fractions that have intelligence? Let's say if you have life, let's just say somehow life happened, ever how rare you think it should be. How many people think that the fraction of those worlds will have involved intelligent life? Who thinks that the number is bigger than 50%? Okay. Who thinks the number is bigger than 10%? Okay, good. Don't be shy. That's cool. Okay. They're starting to get there, but that's at the high end. So the optimists are sort of around 10%. Who think that it's 1%? Who think that it's less than 1%? Okay, some people are not voting. Let me ask again. Who thinks that the fraction of worlds that have life, okay, of the worlds that have life, the fraction that evolve intelligent life is less than 1%? Okay, who thinks that it's greater than 10%? Okay, who think that it's somewhere between, somewhere less than 5%? Let's do that. Okay, so the number we're getting is pretty small, and it's actually somewhere in here. Who knows, right? I don't think anyone knows. I think it's, for the people who are optimistic, which in this case means 10%. For the optimists, raise your hand again, more than 10%. All right, talk to me about why you think that's going to happen. Someone who doesn't usually speak. Let's go in the back row. Why?
Well, I think it's definitely possible. I think the chance of us finding it or getting to it will be really
Okay, okay. So that's an interesting point. You're like, I think it's definitely possible that it's there. The chances of us finding it might be 0, but you think it might be there. Okay, that's totally fine. Does anyone else have any reason why they think intelligent life should be common? Like, why would it be common? Yeah. Or 10% common. Yeah.
I think the hard part is making the planet habitable. Getting intelligent life, that happened fairly quickly.
Well, it took 4 billion years.
That's not bad for it.
That's not bad. Come on.
With after the life actually started, it wasn't that big of a thing.
Okay, so you're more impressed by life itself than intelligent life.
Yeah.
You're not that impressed by us. You're more impressed by the life itself. Okay. Anything else? Any other thoughts on this? I mean, I have nothing intelligent to say about it, so I'm hoping someone here does. Okay. Right, so we don't know. So here's another thing to keep in mind. Imagine you do have your 1%, 0.1% chance you get your intelligent life. What does that mean and what's going to happen with that? Okay? Now, let me remind you that most of the stars in our galaxy are old, much older than 1 billion years. In fact, there are lots and lots of stars in our galaxy that are older than the sun and that are older than 10 billion years. Okay? So at some point in time, one of those stars in its history, even if it was the 1% of the 1%, right? One of those stars gets an intelligent civilization, advanced civilization, emerges on it. That civilization has a huge head start on us. And what will happen? Okay? So, one of the arguments you can make is that any advanced civilization, if it's sufficiently advanced, that is, imagine our trajectory for the next 100,000 years. Okay? Imagine what we will be doing, not in 1,000 years, in 100,000 years. Okay, imagine what our civilization could be capable of in 100,000 years. Okay, that's sort of what I'm thinking about. An advanced civilization of that kind will likely have spread out over a large volume of the galaxy. And let me explain why. So, a rough volume of our galaxy, you can approximate our galaxy as like a cylinder, a little short, fat cylinder. Okay? The volume of a cylinder is just its radius squared times its height times a pi. The radius is about 50,000 light years. Its height is about 1,000 light years. Therefore, its volume is something like 10 to the 13 cubic light years. That's the volume of our galaxy. You might say, boy, that's a huge volume. How could any civilization spread throughout that volume? However, if our galaxy actually does contain 350 civilizations, which is my first rough estimate based on nothing, that's one civilization per 22 billion cubic light years. The average distance between stars that are communicating would be 3,400 light years in that case. That seems like a far way away, right? 3,400 light years. But these civilizations have been around for billions of years. So 3,000 years out of 1 billion years is not very long to send a signal and send one back. Okay? So exchanges of messages would take 7,000 years. But if they find each other, they can start sending messages back. That's totally within the realm of what's reasonable. Again, because you have civilizations that have been around for more than 1 billion years in principle. Okay? However, the distance between stars with habitable worlds might be as small as 20 light years. So what this means is that if you want to find your nearest civilization, you've got to send a signal, and it takes 7,000 years to receive it. But if you just want to go to the next habitable planet and hang out and build a colony and explore, that's only like 20 light years away. And if you can travel anywhere near the speed of light, you can get there. Okay, are there questions about this? So once you have a civilization that develops fast spaceships, and in this case, we're talking fast as like more than 1% the speed of light. And again, that's way faster than what we can do right now. But again, imagine ourselves 100,000 years from now. This doesn't seem out of the realm of possibility, right? The time needed to actually colonize the whole galaxy is much less than the age of the galaxy. Okay? Even if you have a Drake equation with super, pessimistic ideas about whether you get life and intelligent life, as soon as you get that one civilization, that civilization is probably going to be able to colonize the galaxy in a reasonable amount of time compared to the age of the galaxy. And let me explain how that works. Well, I'll explain how that works in a second. But this general idea that it wouldn't be that hard for a civilization, an advanced civilization, to colonize a galaxy is what led to one of the most famous sort of paradoxes in this general field, and it's called the Fermi paradox. Okay? The Fermi paradox is named after this guy, Enrico Fermi, who's a very famous physicist. And the basic point of the Fermi paradox is, where is everybody? Okay? If you think that intelligent life is even remotely a possibility around a star, you begin, if you start working out the numbers, you can realize it's weird that we haven't been visited. Okay? So the Fermi paradox specifically is the apparent contradiction between the estimates of the speed of colonization of the galaxy and the lack of evidence of extraterrestrials. And more general, you know, whether that means they've come to visit us or they've sent us signals. Okay? The point is that the stars in the Milky Way are old, and half of them are older than the sun by at least 1 billion years. Okay? Even if intelligent life happens only a few times per galaxy, okay, we'd be relatively new in the scheme of things, right? We haven't really been doing things that you would characterize as advanced civilization for more than 50 years. Whereas these stars have a billion-year head start on us, right? So now we're not talking about us in 100,000 years. We're talking about us not in 1 million years. We're talking about us in 1 billion years. Okay, so imagine how advanced that might be. So where are our billion-year advanced galactic cousins? Where are they? Let me convince you that colonizing the galaxy isn't hard. So this is, let me just show, this is the Fermi paradox. The story with this is kind of interesting. So how he came up with this is he's this Italian-born physicist. He's one of the primary developers of quantum mechanics. He was one of the leaders in the Manhattan Project. He was alive, you know, during World War II, and so all the physicists who were in this country basically got incorporated to work on the Manhattan Project. So he was at Los Alamos working on the first atomic bomb, and along with a bunch of these other physicists, and they were walking around. They were walking out from lunch, and they were actually looking at the first, like, Take Me to Your Leader cartoon. It was a cartoon in the New Yorker that came out about that time. And they were kind of joking about it and laughing about it, sort of making fun of people who believed in extraterrestrials. And he stops in his tracks. And he was famous for being able to do these complex calculations in his head very quickly. He does these order of magnitude calculations really fast. He was famous for that. So he gets out and he stops and he stands still for a second. And he looks up and he says to the people he's having lunch with, "Where is everybody?" Because he had done this rough calculation of how long it should take a civilization to colonize the galaxy. And he realized immediately that if they were advanced enough, they should be doing this easily in the age of the galaxy. So the way to think about it is, our galaxy is at least 10 gigayears old. Okay? And so, yeah, here's the New Yorker cartoon that he was looking at. Okay? So the point is that when you talk about, when you have a colony, when you have a colonization idea, it's sort of an exponential process. And so the way it goes is like this. Imagine you're an advanced enough alien civilization that you can send a sort of a spaceship to your nearest habitable world. Okay? Even if you're traveling at 0.01 C, you know, it'd take about 2,000 years to get there. But again, you're talking about a civilization 1 billion years from now. This is something that could be done. Even if your lifespans aren't that long, you can just have sort of an arc, right? You just have multiple generations on the spaceship. You get to the next world, okay? Then say you sit in that world for 5,000 years. Seems pretty generous. You build up a whole colony there on that world, harness its resources, build new spaceships, and then you send out another spaceship. But now, rather than just going to your nearest single star, you go to the 2 nearest stars. You go 2. Right? Why not? Why only send 1? Why not just 2? So now you've sent 1 to this world and 1 to that world. You might argue, why would you do that? Well, think about like what happens like with us, right? If anyone finds something interesting over there, okay, let's say you find a gold, you strike gold over here in this mountain. Not everybody's going to go to that mountain and look for gold. Everyone's going to be like, I want to look for gold too. I'm going to look over there. And so there's sort of a natural tendency to just do things multiple times. And so what you get is sort of an exponential process, that you send one ship out to the nearest planet, you create a colony there. If that just launches 2 ships to get to the next planet, wait 5,000 years. That planet, you launch 2 more ships, it becomes exponential, right? So you've got 1 ship, then you've got 2 ships, then you've got 4 ships, right? And it becomes an exponential process, okay? And so when you have colonization like that, it's an exponential process. It's extremely rapid. Okay, so here's your home planet, step 1. Then you have step 2, and each one has a node of 2. And then eventually you can colonize the galaxy. If you do this, right, if you assume traveling at 0.01 the speed of light, 2,000 years between planets, 5,000 years before dispatching next ships, you colonize the galaxy in 100 million years. It doesn't take that long. Again, galaxy's 10 billion years old. So 100 million years is kind of nothing in the scheme of things for this. Okay? Now, the problem is we don't have any evidence that this has happened, that this supposed colony, right, this advanced civilization that supposedly colonized the galaxy, we have no evidence that they visited here. Okay? Nor have we found alien artifacts, despite what occasionally you'll read. There's no good evidence of anything of this kind, right? Okay. So the point of this whole thing is that because the Drake equation ignores colonization, anything you put in the Drake equation probably strongly underestimates the number of intelligent civilizations that you might see throughout the galaxy. And so this goes back to Fermi's question, which is, where is everybody? Why hasn't this happened? Are there any questions or concerns with this? Like, people are like, I don't understand what you're saying. I don't buy this. Do people get it? Do people understand why this is potentially disturbing? Maybe. Okay. Now, of course, there's a number of solutions to the Fermi paradox, right? You could think about, well, what's wrong here? What's wrong with any of these assumptions? So we can sort of step through them and think about what they might mean, okay? So one is that we're just alone, right? And, you could think of this as, sort of like there's something called the rare Earth hypothesis, okay? We've always been alone. Okay, the Earth is extremely rare. The conditions were just so, They were just so in the beginning. Even life getting started was hard. And what are the odds that you're going to get this random string of events to give rise to intelligence? Like, had the dinosaurs not been knocked out by a meteor, we wouldn't be here. It was just sort of this weird luck. So it's just a rare Earth thing. Another idea is that because civilizations blow themselves up, or some other catastrophe happens, right? It's sort of the doomsday hypothesis, that if you evolve to a point where you're intelligent enough to extract energy from your environment and do things, you will inevitably screw up at some point and you blow yourself up, and then there's nothing interesting after that, right? The other idea is that nature just eradicates us, right? We're going to get hit by a big asteroid at some point. There's going to be a global catastrophe of some kind associated with nature that just kills you out. So you just can't live for 100,000 years. Civilizations just don't last that long. A second one is that, look, civilizations just simply have not colonized the galaxy. Okay? This idea that technology is going to continue to increase forever, okay, is just wrong. It's not going to happen. There's no Star Trek future. Okay? That's not in the cards for us. Okay? We're going to go to the moon. Maybe we'll go to Mars. If we're lucky, we might just barely sort of crawl to the nearest star. But that's it. There's some wall. There's some ultimate wall that technology hits. Maybe it's an energetic wall. Okay? Maybe we just can't figure out how to harness energy in that effective way. Okay? Or maybe it's just because most civilizations just don't want to do it. Okay? There's a lot of people here on Earth that are like, why would we want to go to Mars? Why would we want to go to the moon? That's a waste of time. Like, we got enough problems here, right? So why would we want to spend resources and energy colonizing a galaxy? So maybe that just doesn't happen. It's not a common thing, okay? Another interesting one, right, is called the zoo hypothesis, right? That civilizations have in fact colonized the galaxy. They're all over the place, okay? But they just don't want to tell us that they're there. They don't deem us interesting enough to contact. You know, we haven't hit the level of sort of advancedness, whatever, that we're even worth contacting, right? We're like ants or something. They're just sort of looking at us like, huh, that's weird. Isn't that cute, you know, with you know, whatever, their little spaceships, right? Or the other option is that in fact, we do have evidence and the government won't tell us. That's the UFOs are real hypothesis. This is the crazy hypothesis. This is totally crazy. This is not true. If you've ever worked in any government agency, you realize that nobody can keep a secret about anything, much less a UFO in the room next door, right? It doesn't happen. You know, they can't keep a secret about like basically anything. You know? So this is sort of crazy. I think this is just completely nuts. People often ask me like, boy, you as astronomers, like, do you guys know that there's really aliens out there? It's like, boy, if any astronomer found any evidence that there's an alien, they would just immediately broadcast it, right? There would not be this, we're not incentivized in any way to cover anything up, right? Right? Imagine how rich I could be if I discovered an alien. Like, there's just no, you know, like there's no incentive to cover it up at all. So this is crazy. This isn't true. Okay. So why else? You know, look. What's the evidence that we have UFOs, right? Fuzzy photographs, some anecdotal pictures from space, stuff like that, right? This is probably not going to happen. And you notice that since the era of that everybody has a digital camera in their pocket, the number of UFO sightings has not gone up, right? It was crazy. There was all kinds of UFO pictures back in the day when like cameras were rare and pictures were fuzzy. But now that everybody's got a camera in their pocket, it's not like suddenly like, oh yeah, there's UFOs everywhere. If anything, it's gone down, right? So this stuff is crazy. Like this is just, there's no evidence of this, right? So anyway, that's my opinion on that. It's crazy. The zoo hypothesis is kind of fun to think about, right? This is sort of an optimist hypothesis, right? That there is a Star Trek future. That 100,000 years from now, we are going to be extremely advanced, right? And we're just not there yet. And they know we're here, okay? And they just deem us too primitive, or that it would screw us up too much as a civilization to let us in on the big secret now. This is also kind of a conspiracy hypothesis too. But anyway, you know, some people like this. And you know, people talk about, another idea that people talk about sort of in this vein is that, is it a good idea for us to be broadcasting our presence out throughout the galaxy, right? Because we're almost by definition not the most, if there are other advanced civilizations out there, we are probably the least advanced, right? Because we've only been sort of advanced for 100 years. So, you know, if you look at the history of the way these kind of these things have happened on Earth, like it doesn't go so well for the civilization with less technology encountering the civilization with more technology. It usually doesn't end well for the less technology civilization, right? So there are people who argue that like we really should be hush-hush about our presence here. Okay. The doomsday hypothesis is interesting, and you know, it's just that we don't have 100,000 years, right? That there is some ultimate sort of sticking point to how long civilizations like ours can exist. Okay, and whether we're going to get a Walking Dead kind of situation, unlikely. But whether it's, you know, maybe it's just something more gradual, that, you know, there's sort of a peak of sort of being able to sort of tap into sort of very rich energy sources and then do things, and then at some point, you know, we're just going to hit a wall and not be able to sort of send stuff out to the nearest stars, and then that's sort of it. The natural, you know, sort of doomsday comet hypothesis thing is definitely sort of an interesting one, right? You know, over the history of the Earth, right, there have been situations like the snowball Earth stages, where through a series of sort of different events led to the Earth being covered by basically massive glacial ice sheets. You know, all the oceans were frozen. if some kind of massive geological thing like that happened, some sort of global thing that had to do with the Earth and sort of big things, there's very little we could do about it, right? So you'd have to be pretty advanced to be able to save your civilization from something like this. And then your technologies would just fade out because you would just be spending all your energy just trying to stay alive, right? So there's ample precedents for things like this over Earth's history. A number of mass extinctions have occurred over the last 500 million years. And so when you're talking about these sort of billion-year timescales for colonizing the galaxy, maybe this is something that you have to think about. Finally, there's this rare Earth hypothesis that we are extremely unique. We are this unique civilization that exists only because, for example, we're in the right part of the galaxy, we're around the right type of star. Maybe photosynthesis can only evolve in a star like ours. Maybe there's not an easy way to make it happen around a star that's emitting mostly IR light as opposed to visible light, right? We're on the right kind of planet that's half ocean and half land. That's not exactly common, right? If we had twice as much water, there would be no sort of land. The whole ocean would be a water world, right? That's a very different kind of world. We also have a large moon. The moon stabilizes our rotation. It affects the ability for sort of big rocks to hit us, etc. And finally, complex life took a long time, and intelligent life took even longer. And so you had to have, all of these, you had to roll the dice, and you're getting double sixes every time, right? Again and again and again and again. And finally, luckily, this sort of civilization emerges that's just a unique situation. This would say, an argument like this would say, we are the only intelligent species in the galaxy. And let me remind you, all evidence points to this being the answer, right? We don't have evidence that there's any other intelligent species in this galaxy. If you think about that, I'm not saying that's the right answer, but if that were true, that would be a very interesting situation for us, right? Because that would mean, as far as we know, we are the only instance of some combination of events occurring in this universe that has led to the ability to look back out at the universe and contemplate its existence. Right? So in that sense, we're sort of the example of the universe understanding itself, looking back at itself, understanding its origins. Right? So you can think of it as that being a tremendous responsibility. And we don't know that's true, but it could be true. Another thing I think it's very interesting that you have to think about, is that, it's not obvious that an advanced civilization would want to colonize the galaxy. Okay? There were plenty of advanced civilizations that existed over the history of the Earth, that decided not to colonize the Earth. Okay? And these ideas of sort of the monastic lifestyle, you're sort of more introspective, for example, and you get more knowledge out of sort of thinking about inner things or contemplating the galaxy as opposed to traveling through it, could be something like a priority of one of these civilizations, right? I mean, we have enough time trying to understand the culture of other humans, right? You grow up in one culture, understanding another culture is hard enough. You're exactly the same species. Your DNA is identical, right? But you just grew up in a different place and you speak a different language and you can't understand them. You have trouble sort of finding commonality of cultures. Imagine trying to understand the motivations and cultural aspirations of another species entirely. Like, not even just another species, that's something that might not even have DNA, right? Something that would just be entirely different. Trying to understand what the motivations of this kind of species would be is something that's hard. And so you have to keep in mind that they just might not be interested in this kind of stuff for lots of different reasons. Okay. Now, Another idea is that, sort of speaking about the sort of energy requirement argument, that we run out of energy, right? And so it's going to be very expensive to send humans to other star systems. An idea, though, that has come out is that, well, it's actually not that expensive to send robots to other star systems. Even if it takes 2,000 years to get this robot to the other star system, the robot can hibernate, right? It doesn't have to live, okay? And so getting it there might not be a problem, and then you sort of have robots colonizing the galaxy. And there's this idea of self-replicating machines, okay? So in 1948, John von Neumann proposed the idea of self-replicating machines. So robots that are basically pre-programmed to replicate themselves. And so then you have this idea of you can colonize the galaxy with just machines. They can colonize the galaxy, teach you things about the galaxy without having to overcome the physical limitations of people sending them there. This makes a lot of sense, okay? And so there are sort of extensions of this idea that are associated with artificial intelligence. But basically, because of these ideas, it sort of even makes the Fermi paradox worse. Some people have thought about the idea that there might even be such probes in our solar system monitoring us right now, right? Sent from another star system, orbiting in the Kuiper belt or something, and just kind of monitoring us and sort of watching out and seeing what we're doing, without actually having to have direct contact with the life form. They're really sort of a machine life form. Okay, I'm not going to talk about these probes very much. So the thing I want to talk about next time is the search for this life. So I've talked about now the idea of what might be there, what does it mean if it's not there, what if it means if it is there. The last lecture is going to be looking for this life. And I'm going to be talking about looking for very simple life and also the search for extraterrestrial life as we know it now. Okay, thanks.